Well, this video is for Math 111, and I'm going to go over the problems on the sample final exam. Your final will have the same number of questions, the same types of questions, but slightly different questions. Alright, so let's see here. The first page is problems from test number 1. And this was all in chapter 1 of the textbook. So problem 1, we start out 2 times x minus 3 squared minus x plus 1 times x plus 7. So we've got a couple different things happening in this problem. You've got a binomial that's getting squared. You've got a subtraction of the multiplication of two binomials. That's a little bit tricky. And also this 2 is going to get multiplied by whatever we get after we square the x minus 3. You're not going to be squaring the 2. So let's go ahead and do that. 2 times x minus 3 times x minus 3. So this will be x squared minus 6x plus 9. And then here, we'll keep the parentheses because this negative sign is going to change all of the signs inside the parentheses. This will be x squared plus 8x plus 7. So now we're going to distribute the 2 into this parentheses and the minus 1 into these parentheses. So this will be 2x squared minus 12x plus 18, and then minus x squared minus 8x minus 7. So we'll end up with 1x squared minus 20x, and then plus 11. Okay? All right. Let's look at the next problem. I believe that one is a complex fraction that we're going to have to simplify. Yeah, so problem 2, we've got 1 minus 7 over x on top, and then x over x plus 1 minus 1 over x minus 3 on the bottom. Okay? So let's make some common denominators up here. This is 1 over 1, and our common denominator will be x. And then we'll end up with, what? X minus 7 over x. Okay. On the bottom, the common denominator is going to be each one of these multiplied by the other one. And so we'll end up with a common denominator of x plus 1 times x minus 3. So to do that, we've got to multiply this one by x minus 3 over x minus 3, and this one by x plus 1 over x plus 1. And so as a result of that, we get, let's see, x times x minus 3 minus 1 times x plus 1, or just minus parentheses x plus 1. So the top stays the same, and then on the bottom we get x squared minus 3x minus x minus 1, and then x plus 1 times x minus 3. Let's see here. So what do we end up with? X minus 7 over x, and then this will be x squared minus 4x minus 1 over x plus 1 times x minus 3. Now a lot of times I set this up so that you've got some canceling to do. In this problem, that ends up not being the case. Nothing actually cancels here. This x squared minus 4x minus 1 isn't factorable, and this x is not going to cancel with anything, and none of these are going to cancel with anything. So all we end up with here, x minus 7, x plus 1, x minus 3 on top, and x times x squared minus 4x minus 1 on the bottom. If you want to multiply all those out, you can, but I wouldn't recommend it. It's kind of a waste of time. Okay. All right, that's problem 2. Let's see here. Problem 3. we've got two algebraic fractions set equal to each other. This is a cross-multiplying problem. We start out x minus 4 over x equals 1 over 2x plus 1. Okay, so let's cross-multiply. We'll say x minus 4 times 2x plus 1 equals 1 times x. This will be 2x squared, let's see, minus 8 and plus 1, so minus 7x minus 4. And then move this x over here. 2x squared minus 8x minus 4 equals 0. And let's see, if we run this through the quadratic, what do we get? We get x is approximately 4.449 or negative 0.449. Okay, that's problem 3. Problem 4 is one of these rational equations where we have to make common denominators. 1 over x minus 5 plus 1 over x minus 1 equals 5 over x squared minus 6x plus 5. Okay, so the way this is set up is that these are prime, this is factorable, and it factors into the product of these two binomials. So this is our common denominator right here. This fraction is not going to change. It's going to stay the way that it is. Over here, we're going to create a common denominator. This one needs to get multiplied by x minus 1 over x minus 1. And this one gets multiplied by x minus 5 over x minus 5. So we end up with x minus 1. I'll put the times 1 in there. And then 1 times x minus 5. I could have just written x minus 1 and x minus 5, but in other problems, it'll be important to multiply whatever's here by what's in the parentheses. In this problem, it doesn't make a big difference because what's here is 1. Okay. So, there's our setup. Next, we're going to clear out the denominators, multiply on both sides by x minus 5 times x minus 1. Those cancel, and what do we end up with here? We end up with x minus 1 plus x minus 5 equal to 5. So, again, this is Algebra 1. Don't forget how to do this, please. 2x equals 11. X is 11 over 2, or 5.5. Either answer is acceptable. Okay, that's all the stuff from Chapter 1. On the next page, we have a bunch of problems from Chapter 2. So let's see here. Problem 5. What do we have here? 8x to the third plus 2x squared plus 30x minus 27 equals 0. Okay, so let's go ahead and graph this. And this is one of the ones where we want to graph it, find the root, do the synthetic division, factor the polynomial, and find the complex roots. So, first thing we're going to do here is to graph this. Plus 30x minus 27. So, let me show you what it looks like on the calculator. So there it is typed in, and then if we go to our standard window, there's our graph. We'll do second trace number 2. Let's see, a good left bound. I'm just going to type in 0 as our left bound, and then 2 as our right bound. And there's the 0 at 0.75 or 3/4. Okay. So we've got one solution here. X equals 0.75, which is 3/4. So that means 4x is equal to 3. And one of our factors is going to be 4x minus 3. Okay, well now let's do the synthetic division. And we'll do that with 3/4. So that would be 6, 8, 6, 36. 3/4 of that is 27. There's our 0 remainder, which we should be getting so long as this is a root. And then what's left here, remember that we've got the common factor of 4 that we need to get rid of. So this is 2x squared plus 2x plus 9. And then we'll run that through the quadratic and get our complex roots here. So complex roots are going to be negative 0.5 plus or minus 2.062i. So 2 complex roots, 1 real root, and there we go. That's number 5. Okay. Let's take a look at number 6. Number 6. 10x to the 4th, 33x cubed, 12x squared, 11x plus 6. Okay, well let's see. Let's take a look, see what this graph looks like. Alright, the 4th, 33x cubed, 12x squared, 11x plus 6. And again, I encourage you to double check what you've typed in there to make sure that you haven't mishit any keys. Okay, so there's what it looks like typed into the calculator. And there's our graph. We've got 2 roots. It looks like there's a root at -3. Maybe we can save some time and just look in the table. I gotta set my table up. There we go. So yeah, when x is -3, y is 0. Okay, so we know we've got a root at -3, and then we'll go find that other root using the 0 function. Let's see, there's a left bound, there's a right bound, and that root is -1/2. Okay, so we've got 2 roots, one at -3 and one at -1/2. So x equals -3, x equals -1/2. So one factor will be x plus 3. Another factor will be 2x plus 1. And then we'll do the synthetic division to find the missing factor. All right, let's see here. So 10, 33, 12, 11, and 6. Okay. I'll do the -3 first. -30, -9, -6. There's our 0 remainder. And then I'll put the -1/2. half here. -2, +1, -2, and again, 0 remainder. Then we'll pull a common factor of 2 out of here. So this will be 5x squared minus 1x plus 2. And if let's run that through the quadratic and find out what our complex roots are. Uh, 0.1 plus or minus 0.624i. 2 complex roots, 2 real roots. We're all done. And also, don't forget to have the factorization for the polynomial as part of your answer. All the roots, all the factors. That's what I'm looking for. All right, let's see here. Problem 7. This is one of these polynomial inequality problems. Let's see what we're working with here. X cubed minus 7x squared plus 5x plus 12. And we want to know where is that going to be greater than 0. Okay, so let's go ahead and graph this. X squared plus 5x plus 12. Okay. And I'll draw a little sketch, and then I'll show the calculator to the camera as well. Kind of like this. So, we're interested in these 3 roots right here. Okay, so there's what we're working with. I'm going to go back up to the board so I can write down the roots as I find them. Okay, let's see here. So that one is negative 0.954 right here. And then the next one, let's see what we get. 2.179, and then over here, 5.774. Okay, so we're interested in where are the y values greater than 0, positives. Where are the y's positive? That's going to be here and out over here. Make sure you're clear on whether you're looking for positive y's or negative y's before you answer the question. Let's see. So our answer here will be x less than 2.179 but greater than negative 0.954. Or x greater than 5.774. Okay, that's problem 7. Let's take a look at problem 8. So problem 8 is one of these rational inequalities. Where we're interested in finding the roots and the asymptotes. Squared plus 3x minus 2. And this is also greater than 0. That's what we're interested in. Okay, so let's go ahead and look at the graph here. 2x squared minus x minus 1, and then on the bottom, x squared plus 3x minus 2. down there, then an asymptote, and a little piece there, and another asymptote, and then it goes off like that. Okay, so our roots are going to be where this thing is equal to 0. It's not quadratic, so we can't run it through the quadratic formula. And we saw a lot of examples where the top was quadratic. You could run it through the quadratic formula and get the roots. Here the roots are on the graph. We're just going to do the same thing that we did for that last problem, and I'm going to use the root finder, second choice number 2, to go in and find these roots. Because the calculator will always find these roots. It won't, however, find the asymptotes. So that root is negative 2.247 right here. And then the next one, negative 0.555. And then that last one, 0.802. Okay, so now we've got our roots, and then the asymptotes we can find using the quadratic formula. Where is x squared plus 3x minus 2 equal to 0? Okay, let's see here. That's going to be 0.562 and negative 3.562. Okay, so this one is positive 0.562, and this one negative 3.562. All right, so now we've got all of the critical values identified, all the roots, all the asymptotes. Let's answer the question, where is y greater than 0? So that's going to be in between those two values right there, in between those two values right there, and then going off in this direction. Okay, so that is, this one right here is x greater than 0.802, and then we've got this one, x less than 0.562, but greater than negative 0.555, or this last one, x less than negative 2.247, but greater than negative 3.562. And there we go. Got it all. Got all of the regions, all of the intervals where the y's are greater than 0. So that's problem 8. All right, so that's it for chapter 2. And then the last 5 problems have to do with chapter 3. So let's go ahead and take a look at those. Okay, you've got the properties of logarithms on the test paper itself. You can see that on the PDF. And these are very much like the quizzes that we've just been taking for chapter 3. So first off, 8 to the x power is equal to 20. So we can take a logarithm on both sides of the equation. Let's see. I'll use the natural log to start out with. And then this will be x ln 8 equals ln 20. Divide on both sides by ln 8. And so there's our exact value, ln 20 divided by ln 8. And I've asked you to approximate all your irrational values to 3 decimal places. So let's go ahead and calculate here. ln 20 divided by ln 8. Let's try that again. ln 20 divided by ln 8. There we go. 1.441 approximately. And that seems reasonable. 8 to the first power is 8. 8 squared is 64. So somewhere between 1 and 2 is going to be the power that gives us 20. Okay. Let's look at problem 10. here we've got 5 to the 2x plus 1 equals 7 to the x plus 1. Okay. Well, I'll use log base 10 on this one. Let's see here. And so then these exponents will come down in front as coefficients. 2x plus 1 times log 5 equals x plus 1 log 7. All right, well, let's get some good approximations for these. I'll go back at the end and find the exact representation for the answer, but to get us going here, first I'm going to make these approximations. Log 5 is 0.69897 times 2x plus 1. And over here, log 7, 0.8451. Okay, so if we distribute here, we get 0.8451x plus 0.8451. Over here, let's see, 69897 times 2, 1.39794x plus 0.69897. Okay, so let's subtract this 0.8451x on both sides. So those cancel out. Let's see, 1.39794 minus 0.8451. And we come out of this with 0.55284x. And then I'll subtract 0.69897 on both sides. Over here, 0.8451 minus 0.69897, 0.14613, and then we'll divide on both sides by 0.55284. So those cancel out, and what do we get here? Divided by 55284, about 0.264, 0.264. Let's see, we can check our answer, 0.264 plus 1. $11.695, let's say. And then 7 to the 1.264. 11.7. So we're off by a little bit, like 5 thousandths or thereabouts. Okay, so close enough for our purposes. Okay, so those are the two exponent equations. And then we'll have two of these, two logarithmic equations. I forgot to go back and do this in exact terms, so let me just go ahead and do that. If we distribute in here without approximating, what do we get? We get x times 2 log 5 plus log 5 equals x log 7 plus log 7. And again, the structure of the solution is exactly mirrored here. You know, we're going to subtract this on both sides, and then over here we'll get x times 2 log 5 minus x log 7, and then subtract the log 5 on both sides. And over on this side, we get log 7 minus log 5, which is this number right here, 0.14613. And then here, we've got to factor out the x. And then divide on both sides by 2 log 5 minus log 7. So there's our answer in exact terms. Those cancel. So there's our answer in exact terms. If we approximate that, we should get about 0.264. Okay. So there's problem 10 with both of those methods. Like I said, we'll go and take a look at those logarithm equations. There's two of those. Okay, so problem 11. We've got log to the base 5 of x minus 2 plus log to the base 5 of x equals 2. Okay, so we want to consolidate these two statements, these two logarithms, into one statement. Log to the base 5 of x times x minus 2 equals 2. And then we restate this saying 5 to the second power is equal to what's in the brackets or parentheses there. So this will be 5 to the second power is equal to x times x minus 2. So 25 equals x squared minus 2x. And we come out with a quadratic x squared minus 2x minus 25. And so we can run this through the quadratic formula. And we get x approximately equal to 6.099 or negative 4.099. Okay, well, that's problem 11. Let's see. Problem 12. ln 2x minus ln x plus 1 equals ln x minus 4. Okay, so we'll use the property of logarithms to restate this as ln of 2x over x plus 1. The one with the negative in front of it goes on the bottom. And that's equal to ln of x minus 4. And now we can pick these out of here and set them equal to each other. 2x over x plus 1 equals x minus 4. This is saying if their natural logarithms are equal to each other, then the quantities inside that we're taking the natural logarithm of also have to be equal to each other. Okay, so now we want to multiply on both sides by x plus 1. These cancel, that's the whole point of multiplying by x plus 1. That'll leave us with a 2x on top. Over here, we get x squared minus 3x minus 4. And then we'll subtract the 2x on both sides and get a quadratic x squared minus 5x minus 4. And then we'll run that through the quadratic formula and see what we get. And so we get x equals approximately 5.702 or negative 0.702. Okay. One more problem, and this is from section 3.1. This is the first thing that we did in chapter 3, which was to answer one of these application problems by using the graphing calculator. So, let's see what we've got. So, this is about a radioactive isotope of sodium used to study circulatory dysfunction. We've got a graph here, or a function, 4e to the minus 0.0462t. Okay, so that's what we're going to want to graph. I'll draw a little sketch of the graph on the board once I get it set up here. And I'll also show it to the camera so you can see what we're working with. Negative 0.0462x. Okay. So there's what we're graphing. 4e to the negative 0.0462x. And then we hit the graph key. Now I'm still in the standard window. This problem happens to be pretty good in the standard window. We can see a lot of the graph. I'm going to change this window a little bit. I'm going to make my x minimum negative 1. I'm going to go out past 10. Let's say I'll go to 25 or so. And then the y minimum, I'll make negative 1, and I'll make the y maximum 5. Because our graph actually starts at 4. So that shows us a lot more of the graph. That's a little bit better picture. Okay, so that's what I'm going to work with there. And I'll label the maximums and minimums for the window on the board when I draw a little sketch here. Okay. So, let's see, there's our axes over here, and we've got a graph kind of doing this. And I think the x's went out to 25, and the y's, I just went up to 5 on there. All right, question A, what amount of sodium 24 will be present after 5 hours? So, at t equals 5. There's a bunch of different ways to get this answer. You can look in the table. Let's see here. Let's get a, come on. There we go. So if we look in the table, hit second graph, there's your table. We want to know what's going on at t equals 5. There it is, 3.175. You can also go to the calculation screen and just do 4e to the minus 0.0462 times 5. And there it is, 3.175 approximately. Or you can also go into that calculate menu, second trace. Choice number 1 is find the value. Find the value when x equals 5. There it is, 3.175. You only have to do one of those. Okay? I'm just showing you there's a variety of different ways to get that same answer. I think the table is probably the easiest way to do that. So y is approximately 3.175, and I believe we're in micrograms here, but I'm not going to worry too much about the units. Okay. Part B. How long will it take for there to be 1.7 micrograms? So, let's look at the graph again. So for this one, what we want to do is we want to go back into the graphing window where it has y equals, and we want to graph y equals 1.7, which is the value that the problem was asking about. And there's the intersection right there. If you don't see the intersection, you're going to have to expand your window somehow so that you can see the intersection. Otherwise, the calculator won't find it for you. To find the intersection, right, you want to do second trace. Choice number 5 is intersect. First curve, yeah. Second curve, yeah. Guess. No, I want the actual intersection. And there it is. X equals 18.52. Let me see where I asked us to round on this one. Round your answer to the nearest tenth, so 18.5. So for y equals 1.7, our t will be approximately 18.5 hours. Okay, so that's it. That's the final exam. If you have it, I would encourage you to watch this prior to next Friday, which will be our last day of classes. That's the day I'm going to set aside to talk about the problems on the sample final exam. So I encourage you to watch this before you come to class on Friday. So if you have any questions, we can address them. Otherwise, you can always contact me. I have office hours, and you can email me or talk to me outside of class. Otherwise, I will see you next time. Thanks.